Hello everyone, I'm Zexing. I'm currently a fourth-year PhD student at University of Illinois at Urbana-Champaign. Today, I will present our paper on personalized pricing with group fairness constraint. This is a joint work with my advisor, Professor Xin Chen from Georgia Tech, Professor Yuan Zhou from Tsinghua University, and Zi Shuo. In the big data era, personalized pricing has become a popular strategy which sets different prices for the same product according to individuals' features. Despite its popularity among companies, this practice has been heatedly debated due to the concerns over fairness that can be potentially caused by price discrimination, especially to sensitive attributes like race and gender. Protected groups may be charged higher prices due to their potentially higher valuation per product, resulting in disparity against the protected classes. One popular phenomenon is called pink tax, which is shown in the figure below. We can see that female usually get charged more than male on beauty product and service. Moreover, this pricing strategy is illegal if it discriminates based on race, religion, nationality, or gender. Recent regulations has been made to ensure fairness in the business world, like the treaties proposed by the Federal Trade Commission. So to address these issues, we aim to answer the following two questions through this work. The first is how to model fairness in the context of personalized pricing, and then what is the impact of the fairness constraint. Our work is mainly related to the three streams of literatures. The first is the personalized pricing and price discrimination, which is the context of this work. Typically, we focus on analyzing contextual prices, which is the first degree price discrimination. And secondly, our work is also based on the papers of fairness in pricing. Existing works has already studied non-contextual static and dynamic pricing, while in our work, we consider contextual setting and we also model the fairness regulation differently from the existing literatures. Our work is also broadly related to the algorithmic fairness. We know that several fairness metrics has been proposed in the machine learning world, like the accuracy parity or equalized odds. Well, in this work, we adopt the statistical parity as our fairness metric. Now, let me introduce the personalized pricing framework. We focus on a scenario where a monopoly is selling a product to different customers. The seller has access to each customer's feature vector x tilde, which consists of two parts. The first part is the non-sensitive part, capital X, which includes features like the customer's purchase history and other non-sensitive information. While the second part is the sensitive features such as race, gender, or nationality, which denote as capital S. We assume that the feature vectors of each customer are independent, identically distributed. Although for a specific customer, their X and S may be dependent due to potential correlation between the features. Furthermore, we assume that each customer characterized by the feature vector x tilde have a valuation for the product, denoted as V function, which follows a feature-dependent cumulative distribution function known to the seller. To devise an effective pricing strategy, we introduce the pricing policy row, which maps the customer features to the admissible prices. And the price set, which denoted as calligraph P, is the bounded price set and can be either discrete or continuous. Now, let's delve into the personalized pricing procedure shown as the figure below. So once the seller observes the customer's feature vector, they offer a price from the bounded price set P to that individual. Subsequently, the customer's demand is determined based on their valuation and the offered price. If the valuation is greater than the price, the customer will make a purchase, otherwise they will not buy the product. Ultimately, the seller's objective is to learn a pricing policy row that maximizes the revenue while adhering to a group fairness constraint, which we'll define in detail later. Now, let me formally introduce our model. Our goal is to learn a fair pricing policy that maximizes the revenue. Here, we establish a stochastic formulation shown in equation 1. The objective is the expected revenue, which is the expectation of the product of demand and price taking over the features. To explain the fairness constraint, we define the group membership as a function mapping from the features to the group labels. And in the constraint, the QU is the probability density given by our pricing policy for group U. While the QU tilde is the probability density given by the pricing policy of unconstrained problem. And D is the distance metric, and in this work, we typically consider the total variation distance and the Earth mover distance. And the fairness degree, we define as delta, which is ranging from 0 to 1. If delta equal to 0, it means perfect fairness. If it equal to 1, it means no fairness at all. Now let's discuss the fairness measures employed in our study. In previous work, they have already focused on considering the distance of single price policy or the mean price policy as their fairness measures. However, we take a more comprehensive approach in our study. We go beyond the simple moment-based information and consider the full distribution of the pricing policy. By considering the entire distribution, we capture a wider range of fairness concerns and provide a more meaningful insight. To solve this problem, we reformulate it as a linear programming. In our algorithm, we'll work with a sample of n customers divided into k groups without admissible prices available. The variable Fiju quantifies the likelihood of assigning price Pj to customer I within group U, and the decision variable alpha Ju represents the proportion of customer group U who are assigned to price Pj based on our pricing policy. Our primary objective is to maximize the expected revenue, which we approximate using the samples. Moving on to the constraint, the first one represents the price distribution of customer I in group U. And the second constraint is the probability of taking price J of group U. And lastly, we enforce the group fairness constraint, which ensures that the proportion of customer taking price Pj in two different groups does not differ by more than delta. And this constraint promotes fairness in pricing across different customer groups. To bridge the gap between the discrete and continuous price setting, theoretically, we prove an 1 over L gap between the optimal revenue with continuous and discrete price set of size L. Under some mild conditions of the demand functions, we improve this bound to an order of 1 over L squared. Now, let me show you some exciting experiment results. So we use a real-world dataset from the e-commerce company Jingdong.com, Chinese largest retailer, to demonstrate the benefits of our model. The dataset provided by Jingdong.com offered a detailed view on activities associated with all SKUs within one anonymous category during the month of March in 2018. In the experiment, we used the transaction level data consist of 3 tables labeled as SKUs, users, and orders. We used one top selling product, including around 3,000 customer purchasing histories, with around 2,000 in group 2 and 1,000 in group 1. We select 6 normal features. For example, the user level, the age, the marital status, education, city level, and the purchasing power, and one sensitive feature, which is gender. And we evaluate our benefits of the outcome of model by the customer surplus and social welfare. And we also evaluate the fairness of our model by the Gini index. We all know that in economics, the Gini index is a measure of statistical dispersion to represent the wealth inequality within a nation or a social group. Well, we redefine this Gini index under our pricing setting to be measuring dispersion of the price distribution between pairwise groups. Before we conduct the experiment, we first did some preliminary analysis to justify some assumptions. So from the Kirmy-Grove-Smirnov test, we can tell that the normal features between the two groups have a similar distribution conditioning on the sensitive attributes. We also could tell from the data that the female group had a higher valuation over the product. Thus, it will induce a bias in the initial pricing distribution between the two groups based on the sensitive features, which is shown in the figure B. To correct this bias, we tried different fairness measures. Our fairness constrained pricing model is compared to baseline models in terms of price distribution across two groups, as shown in the figure below. Notably, our model results in a more equitable distribution compared to the mean price constraint and unconstrained model, preserving the diversity in pricing policy while minimizing the revenue loss. These findings underscore the benefits of our fairness model in achieving an optimal balance between the fairness and the revenue potential. Our model also showcases the other benefits of fairness. We can see from the graph below that if we impose stricter fairness regulation, it will lead to higher customer surplus, social welfare, and lower Gini index under some regular conditions. And this analysis guides decision makers in selecting an appropriate fairness degree delta to balance the revenue and social welfare considerations. By comparing a model with other baselines, with the mean baseline is in red and the single price baseline is in blue. As displayed in our figure, our model, which is displayed in a green line, consistently surpass the baseline models in social welfare and demonstrate a more equitable price distribution as affected by the Gini index. It is also worth noting that while the single price constraint model shows a varied performance in Gini index, our model overall sustains better social welfare and equitable pricing. Also, we did analysis on the price discretizations. So we can tell from the figure below that increasing the price discretization under fairness constraint with total variation distance lead to higher revenue. And we can see from the right-hand side graph that the gap of the revenue converges at a rate faster than linear, which proved in the theorem 2. It is preferable to choose a moderate size for the price set, as aggressive discretization may not yield significant reward. So to sum up what I have presented so far, so in modeling, we proposed a stochastic formulation to model the personalized pricing problem for different groups under fairness constraints. As for algorithm, we reformulated this revenue maximization problem with statistical parity constraint into a linear program under sample average approximation. Theoretically, we established an order of 1 over L squared for optimal revenue between continuous and discrete price sets of size L. Empirically, we demonstrate the benefits of the fairness constraints over several baselines. We also provided managerial insight on determining a proper fairness degree and selecting an appropriate size of the discrete price. In this presentation, we mainly discuss the results under the total variation distance. While all theoretical and numerical results could be extended to fairness constraint with Earth-mover distance and also under different demand models such as exponential, logistic, and log-log. There are also other exciting future directions to think about. One is we can try other distance metrics such as the H divergence and the KL divergence. And in the theory part, we can also try to find the lower bound of the optimal gap in the theoretical results. That concludes our presentation. Thank you for your attention. If you have any further questions, please don't hesitate to reach out to us.